So this morning I'm going to talk about effective core potentials for electron scattering. So we're going to briefly look at why I'm looking at this, which is because we want to be able to do electron scattering calculations on heavy atoms. And when we start to do these on heavy atoms, relativity becomes important. And one way to account for the relativity, rather than solving the Dirac Hamiltonian, is to use an effective core potential instead. And we've implemented this in QEC 1.2 for binary Bethe encounter cross sections for electron impact ionization. So we're going to look at germanium hydride at a variety of ECPs, and then look at various other series of molecules and see how this is affecting Bev cross sections. And then I'm briefly going to go through the plans of what we are going to put in QEC 1.3. So we want to be able to calculate electron scattering for molecules containing heavy atoms. And this means that we have to account for relativistic effects. So where do these become important? Well, for these molecules that are highlighted on the periodic table, they're going to be visible effects that you have relativity. So what do I mean by visible effects? Well, relativity makes things gold. So there's the difference between silver metal and gold metal in the color. Also in this ammonium tin chloride versus the lead molecule instead. And again, you get this nice gold color. Again, a difference between sodium NO2 and lead NO2. And again, you get this nice gold color. But it also affects things like your molecular orbitals. So here in this diagram, we're looking at hydrogen-like orbitals, where instead of hydrogen having a mass of 1, we've given a mass of 80. And we look at the 1s, 2s, 3s, and 3p orbitals. And that's shown in these diagrams here. And where the line is solid, relativistic effects have been included. And where it's dashed, they haven't been included. And you can see visible changes to the shapes of these orbitals. So we have this radial contraction and energy stabilization of the S and the P. You also have spin orbit coupling effects in P and D shells. And you also get an orbital expansion and energetic destabilization of D and F orbitals. And all of these effects will grow as Z squared, so they become more and more important as you go down the periodic table. Yeah, so if we wanted to fully account for relativistic effects, we would need to solve the Dirac Hamiltonian for the scattering problem, which would be quite challenging. However, we can use an effective core potential instead. And this allows us to treat the valence electrons only. So all of our core electrons and our nuclei are instead replaced by these potentials, this VCPP and this VCC. And as long as those have been fitted using data that accounts for relativity, then our pseudo potential will account for relativistic effects. Oops. So the benefits of using an ECP are we massively reduce the number of basis functions. So we now only have, we're now only describing valence electrons. So we have fewer electrons, which means also we have less electron correlation terms in any of our Hamiltonians. And also we get this advantage that we can wrap in some relativistic effects. So we should get improved orbital energies and shapes. So this is the Bev formula. And the important parameter in these are T and U. which account for the orbital energy and the kinetic energy, respectively. And it's this kinetic energy term that causes most of the problems when you're trying to calculate BEB for heavy atoms. So what we find is if you just use kinetic energy integrals from Hartree-Fock with no correction, then these are overestimated, and you end up with a much smaller BEB cross-section than you should do. Whereas if you use an ECP instead, these kinetic energy integrals are going to come out much better. So this is the BEB cross-section for germanium hydride. And we can see on this graph various different ECPs, but most of them are all lumped together. So this red line here is the all-electron calculation. So this was performed with CCP-BDZ. Whereas these ones look very colorful and dashed, that's a whole bunch of ECP calculations. So that's where these ECP28, this is the size of the number of electrons that have been removed, and the MWP means that it is quasi-relativistic. Whereas this MDF means that the fitting went on with a Dirac-Fock Hamiltonian. So this is full relativity, but we see no difference between those two. So the largest difference that we see is in actually the size of the number of electrons that you put into the core. So this green line here has a smaller core. So you have more electrons and account less well for the orbital changes due to relativistic effects in the valence. So unfortunately for this molecule, there is only one experimental data point, but we have compared to other theory. This black line here is a NIST result, which is a BEB calculation where the kinetic energy integrals were divided by 3 because to account for this overestimation of the kinetic energy terms. Yes, and the other lines are all theoretical. So the MAR approach is in blue, which is the only one that really agrees with the experimental results. And the DM approach is in green. Yes. So what we also looked at was the series of hydrides, starting with carbon and descending that group. So you can see with methane, there is very little difference between the all-electron calculation, which is in black here, and the red line, which is with an ECP. And this is expected because all of the atoms here are quite light, so the relativistic effects are quite small, and the core size is also very small. It only includes two electrons, the 1s of carbon in the core. And so the next picture is SiH4, and we can see here that the results are more noticeable in the difference between the black and the red curve, and the red curve is getting closer to the experimental data than the black curve is. Yes. And similarly, we looked down the series where there's carbon and different group 7 elements. So fluorine, chlorine, and bromine on the right. And again, one of the things that we notice is there's not very much experimental data to compare with by the time we get to bromine and the periodic table, which is disappointing. But our BEB curves match a lot better with an ECP to the SCOP method for calculating ionization cross sections than an all electron calculation. So you can read much more about our implementation of ECPs with BEB in this paper by Vincent Graves and all. And so I'm now going to quickly go through some of the future plans that we have for QEC. So we'd like to implement ECPs for all of the scattering processes. So this means using them in the calculation with the UK RMOL plus codes. So it really what happens when we swap out this nice water molecule here for something like tungsten 2 means that we are going to have to change how we describe the target molecule in the scattering codes. And basically where it's going to show up is when we try to get rid of our tail integrals. So we have to confine the target to the inner region. Normally our integrals are expressed for the target over all space. So it's how do we make sure that either the ECP is just nowhere near the target boundary, or how do we have to start accounting for that in the maths of what happens on to these integrals. So our first approach is going to be to just simply take 1 electron integrals from MolPro directly, because these will already have the ECP included in them, and just read those in instead of calculating them ourselves, which only works if the ECP is nowhere near the boundary of our matrix box. So what we're also going to be looking at putting in QEC 1.3 is looking at the fragmentation pattern for electron impact ionization. So one of the benefits of QEC over QN is its integration with MolPro, and that means that we can start to do more calculations automatically. So we can start to automatically start calculating some of these dissociation energies, and then obtain branching ratios and use these to calculate partial ionization cross sections using BEB. And again, we've already started exploring this topic, and Vincent has another paper in the pipeline, which hopefully will be available soon, where you can read much more about this. So a few other ideas of what we'd like to put into QEC 1.3 is to use the vibronic frequencies. We're already calculating those for the vibrational frequencies that Maria showed in the first talk. And so can we use these in our dissociative electron attachment estimator? Because currently we just use an estimate of 1,000 wave numbers, or ask the user to input experimental data. So it'd be quite nice to remove some of the difficulties in inputting those numbers in. Yes, and the other thing that we're looking at is to make it easier to obtain quenching cross sections. So the data is currently all there when you run QEC, but it's not presented in a user-friendly way, and so we would definitely like to improve upon that. And with that, I am finished. Thank you very much.